Hello everyone, welcome to my channel and today we will discuss about some another definitions of modern algebra. So we will discuss the another definition. If A belongs to G, then NA, the normalizer of A in G, is the set NA is equal to X belongs to G such that XA is equal to AX. There is a theorem. If Na is a subgroup of G or the normalizer of a group is a subgroup of G. So for proving this theorem, since E belongs to G, then EA is equal to AE for all A belongs to G by the definition of normalizer of A in G. Then E belongs to Na. Thus Na is a non-empty set. Let x comma y belongs to Na, then xa is equal to ax and ya is equal to ay. Now for closure property, prove that xy belongs to Na. For this, xya is equal to xya by associative property. So is equal to xay. Since ay is equal to ya, so xa into y. Since by associate property, ax into y, because ax is equal to xa, then xya is equal to axy, which implies that xy belongs to Na. Now Na satisfy the closure property. For inverse property, prove that x inverse A is equal to A inverse x. Now consider x inverse A is equal to x inverse A dot E. So x inverse A, x inverse, x inverse AX, x inverse by associative property. So we can write x inverse XA, x inverse, then x inverse x, AX inverse, which can be, and this x inverse x can be written as E. So E dot A x inverse, and it can be written as A x inverse. Here x inverse belongs to Na, hence it satisfies this inverse property. Now we will discuss another definition. If G is a finite abelian group, S is some integer, then we define GS is equal to x belongs to G such that x to the power S is equal to E, which implies that e to the power S is equal to E, and E belongs to GS is equal to GS is not equal to phi. There is a theorem. GS is subgroup of G. Since e to the power S is equal to E, so E belongs to GS and GS does not equal to phi. Now let x comma y belongs to GS. So x to the power S is equal to E and y to the power S is equal to E. So GS is equal to G. So G is finite. So GS is also finite. So it is sufficient to show that GS satisfy the closure property. Now it is a subgroup. So xy to the power S is equal to x to the power S dot y to the power S is equal to E dot E, can be written as E. Then xy to the power S is equal to E. xy belongs to GS and GS is a subgroup. There is another theorem जिसका स्टेटमेंट है if G and G dash are isomorphic finite abelian group, then for every integer s, gs and g dash s are isomorphic. Okay, so इसका proof है obviously a mapping phi such that g tends to g dash, which is 1 1 homomorphism. It is also 1 1 and homomorphism in its subgroups. GS and G dash S. First, we shall prove that phi GS is a subset of G dash S. Here, it is sufficient to show that phi GS is equal to G dash S. Now, there's this line, phi GS is a subset of G dash S. Let X belongs to GS, then phi X belongs to phi GS. Since X belongs to GS, then X to the power S is equal to E. Since X belongs to GS, then X to the power S is equal to E. Now phi X to the power S is equal to phi X dot phi X and up to S times. So it can be written as phi X dot X dot X up to S times. And it can be written as phi X to the power S. So x to the power s की जगह हम लिखेंगे e. So phi e is equal to e dash. So phi x to the power s is equal to e dash. So phi x belongs to g dash x. Phi gs is a subset of g dash s. Now we shall prove that g dash s is a subset of phi gs. Let u dash belongs to g dash s. Now we shall prove that G dash S is a subset of phi GS. Let U dash belongs to G dash S. U dash belongs to G dash S is a subset of G dash. U dash belongs to G dash since U dash is equal to phi Y. So E dash is equal to U dash to the power S is equal to phi Y to the power S. Here phi y अप टू एस टाइम्स. सिमिलरली जैसे हमने यहाँ पे एक्स के लिए किया था, हम यहाँ वाई के लिए करेंगे. सो फाई वाई डॉट वाई अप टू एन टाइम्स, सॉरी एस टाइम्स. नाउ फाई वाई टू द पावर एस ई डैश इज इक्वल टू फाई वाई टू द पावर एस. बट phi e is equal to e dash, then phi e is equal to phi y to the power s, then y to the power s is equal to e. Y belongs to g s. Here phi y belongs to phi gs. Here u dash belongs to phi gs. G dash s is a subset of phi gs. So g dash s is equal to phi gs. Phi is on to G dash S. Hence, G dash S and GS are isomorphism. Hence, proved.